Tonight, I would like to introduce Shobho Bhattacharya, who is going to introduce our speaker. And once again, thank you all for coming.
Good evening. It's my pleasant duty to introduce the speaker of today's lecture, Professor Sidney Nagel, whom I have known for many years, many more than either of us would like to admit. In fact, he used to be my boss at one time, and this is my chance to get even. The first and the most important thing you must know about Sid Nagel is that he is a fan of the Chicago Bulls. And when I saw this videotape, I thought it might be a Michael Jordan video. But he assures me that it isn't. Sid was born in New York City, and he grew up there. He got his undergraduate education at Columbia, and then did his PhD at Princeton. And after a postdoctoral stint at Brown, he went to University of Chicago, where he's now the professor of physics, and at the Department of Physics, and at the James Franck Institute. Going over his scientific career, I noticed a very interesting pattern. Sid has a lifelong interest in disorder. It may have something to do with being from New York City. And there is a very interesting evolution. He started his career looking at electrons, very small particles in disordered metals. From there, he moved to atoms and molecules, considerably bigger things, in disordered systems that we call glasses. Then he made a further leap, and he has been looking at granular materials, like a grain of sand, which is made out of these atoms and molecules. And from there, he went to sand piles and avalanches in sand piles. And lately, he has made a rather gigantic leap from there to the structure of the universe. William Blake saw the world in a grain of sand, and therefore Sid needs a sand pile to see the entire universe. He is a very distinguished member of our community. His work has always been marked by simplicity, elegance, imagination, and what we generally call creativity. And we are extremely pleased that he accepted our invitation today to deliver this lecture. Sid Nagel.
Well, thank you very much, Shobho, and you indeed did get even tonight, and there's still more years left in front of both of us, I hope, for us to turn the tables one more time. I'd like to talk tonight about the physics that occurs in a sand pile. And when I say this, you might think at first that this is a rather trivial subject and too simple and not very important. And I want to assure you that I don't think it is any of those things, that it's a very rich subject full of a lot of fascinating phenomena that we're only beginning to understand or see, and they're really very poorly understood, certainly at a basic point at this point. Now, part of what I want to do in this lecture tonight is to give you a glimpse of what some of these, what I find fascinating phenomena are, and that's going to be one goal of this lecture. A second goal of this lecture is going to be to try and show you how sand has been used as a metaphor for other areas of physics. In particular, there's been a theory a few years old now which tried to relate the avalanches that you see in a simple pile of sand to the physics that occurs in a lot of different kinds of phenomena. Indeed, so wide a range of phenomena that it's supposed to include trying to understand the large-scale structure of the universe, what's called fractal nature. Now, this is another motive for this talk tonight. What I would like to get across is tell you a little bit about what that theory is and what the results on sand have to do with this. But before saying that, I should also emphasize the fact that sand is really a very important material. Granular materials as a whole are very important. And we see it all around us, and we tend to forget how important this is because it doesn't seem like a high technology field. So you go out on the roads And the roads are made by people bringing in large quantities of sand and gravel, which are granular materials. And we have to learn how to move them and handle them and process them in order to make these roads, dams, buildings, levees, etc. So that's one place that we see this. Another place, which is more at home to me in Illinois, is all the grain. The agricultural community depends on being able to process grain. And you see these large silos at the side of the road, which is all housing this grain. And these silos sometimes just break apart due to the stresses that come into it because of the grain flowing out the bottom. So the agricultural community uses this. Mining, of course, uses it. The ores from mines are involved using granular materials. The pharmaceutical industry processes powders and pills, and so that's something that's used. Around here, you see screes at the bottom of your mountainsides, and this, again, is just granular material that's fallen down from the mountains, and so this is a geological phenomenon. So sand, granular materials, is a very important material that we see all around us, and we have to use, and we have to learn how to use it properly. Now, the plan of my talk tonight is to start off with telling you what is the word fractals in the title. That is, when I told you that this model for avalanches, do they explain the fractal nature of the universe? I first want to tell you what fractals are and give you some examples of that. Then I want to concentrate on the question of avalanches and why are the avalanches important for understanding something about the fractal nature. Okay, and so that's one part of the talk. And then I want to go on after that and talk about the physics of sand and tell you about all these other wonderful phenomena that occur in these materials that we're just slowly beginning to learn about. All the work that, at least that I participated in, was supported by the National Science Foundation with two collaborators at the University of Chicago, Heinrich Jaeger and Xiu-Heng Liu, were the participants in this work. But I'm trying to give a general lecture, and so it's not all going to be on certainly the stuff that I myself worked on. So what are fractals? It's something that we hear a lot about, and I'm going to use a very simple definition for the fractals. It's not technically the most sophisticated definition, but it's simply saying that a fractal looks the same when viewed on many different length scales. So, for example, if you look at something which has a lot of different structures, and you look at a very small part of it, and you blow that part up, it looks like the whole system itself. So, as I say here, one hair on one finger on one arm looks just like the whole arm. So it's the same scale going lower and lower into the system, deeper, and you probe deeper and deeper. And I've drawn here two examples that I could draw of a fractal that you can begin to see how you set this thing up. This first one is what's called the Cantor set. And you start with a line, and you erase the middle section of the line, middle third of the line, and you're left with two pieces, one piece here and the other piece there. And then, with the two pieces that remain, you erase the middle third of those lines. And so I erase the middle third here and the middle third here. And then, with the lines that remain, I erase the middle third of those. And so I go down to this level. And now I have 2, 4, 6, 8 pieces. Again, I do it again, and I get 16 pieces as I split this thing up farther and farther. And you can continue this thing down on infinitum. Okay. If you look at, let's say, this little section over here, well, let me start with this part here. This little part here looks just like the part that it came from, the whole piece that it came from. If I look at this whole 4 part here, it looks like the entire section over here. And so you see, no matter what scale I look on, it looks like just a smaller version of the whole object itself. So this is one simple fractal object. Another fractal object is a kind of snowflake where I start with a line. I erect on the middle third of it a triangle, an isosceles triangle. On the middle third of each side of this, I erect another isosceles triangle. On the middle third of that, I erect another isosceles triangle. And I can go on and on and on in this. And no matter what scale I look at, this system looks like the entire object. So these are two simple fractals that I've drawn for you. And the question that has really been puzzling a lot of physicists for a number of years is, why are these fractal objects important? Are they important? And it seems like they are, because if you look at nature as a whole and you look at different aspects of the world around us, you see that these fractal objects are ubiquitous. They seem to appear everywhere. So there are some things which wouldn't be so interesting for me to show you. That is, I could take an aggregate and where these particles just swim around, they stick to each other, and you get something that looks larger and larger as the more of these particles stick together. This is something which we know quite well is a fractal. But there are a bunch of other objects which we're somewhat more familiar with and at least make prettier pictures, which also look like they may be fractal objects. Here I have just a photograph of lightning strikes around an observatory in Arizona. And you see that here, if I look at one of these big objects, it has branches coming off of it. And I look at one of the branches, it has branches coming off of it. And this begins to have the feel of what's a fractal object. Now, this is something that happens in lightning. You can see a much better picture of something similar to this, which happens in just a piece of plastic. So the experiment here is you took a piece of plastic about yay big, and you stuck it in front of a high-energy accelerator, and particles just came ramming into this piece of plastic. You left it there for an hour or so, and you're full of charges. The charges just rammed into this. And then what you did was you discharged this piece of plastic to ground. And suddenly all the charge that was contained in this piece of plastic now had to get out of there as quickly as possible, and you got something which is called dielectric breakdown, where the plastic just kind of got ripped apart by the electrons trying to leave this object and get to the ground point. So I have some pictures of that, and what I've shown here at the top scale, let me bring this down just a bit, is the whole object. This is that object which was roughly this size that I told you about. And this is where the ground plane was. The whole thing was relatively evenly covered with charge. And you see how it just rips all the charge out of this, and it creates these pathways that you can see after the charge is left. And it has this finger-like structure with fingers within fingers. And what I've drawn, just photographed down below, is a blow-up of one little section of this object on top. So it's the same object, just at a higher magnification. And here again you see that these branches keep going down farther and farther. Here's another branch, and this branch has little branches coming off, and these little branches have smaller branches coming off, and those seem to have smaller branches even within them. So this is something akin to the lightning strike that we saw, but something where we see a much wider array of length scales coming into the problem. Okay, now let me also show the first, where is it? First slide here. Okay, now this is a slide which looks like things that you've seen. Looks like a fern, it looks like dendritic growth of a solid, but it isn't. This is more appropriate for Aspen, because what this is a satellite picture of the mountains in China. And the white stuff here is the snow, and the snow goes down to roughly a certain altitude. And so what you see here is kind of a cross-section at a certain altitude of these mountains. And so this is the height of the Earth. And the height of the Earth seems to have branches in it. Let's see. So here's one branch, and off this branch there are other smaller branches. Off these branches there are smaller ones still. And this begins to look a bit like a fractal object again, just like the previous diagram. But who told us, or what business do mountains have being fractal? Who ordered that? Let me go to the next slide. This is another satellite view. This is of a region near Tibet where you have a fault line. And here again, you see all sorts of rivers coming in. These rivers show one branch branching into smaller branches again. So this, again, I guess you can see it best over here. You see this river-like pattern. And again, if you did the same kind of topological view of this, you would again see something like the previous slide, which showed that the altitude itself also seems to behave something like a fractal. Again, why should these erosion phenomena look like a fractal object with things happening on all length scales? This now is something that has nothing to do with the gross features. This is a small rock that was just fractured by a meteor impact. And here again, you see a lot of small lines within smaller lines within smaller lines where these cracks develop. And so the crack structure in this also looks like it has many fingers within many fingers within many fingers. And so the final slide that I want to show you is this view, which is just a view of the nighttime sky. And here you see that the stars, or the light, is all clustering in regions, leaving other holes. Inside these holes, there are smaller regions of stars. Inside those smaller regions of stars, you get other openings and empty spaces and filled spaces. Again, and again, you have holes now instead of fingers, but holes on all different scales, or globular clusters on all different scales occurring in this structure of the universe. And so this is what I mean when I say what is the structure of the universe we're interested in at least in this lecture, is why should all the matter in the universe be clustered in such a way that no matter what magnification I use, I will see something that seems to look pretty much like the whole universe. That is, if I take a small section of the universe, I couldn't really tell how big a region I was looking at. Okay, so the last example that I want to give of a fractal nature is, especially for anybody coming from California, something that's particularly important, is earthquakes. Earthquakes appear to have all different scales, all different sizes of earthquakes. And so I didn't take California, which is more in the news, but some place a little closer to home for me, which is southern Illinois, which is called the New Madrid Fault area. And this is this is Illinois here, Missouri, Kentucky, Arkansas, and Tennessee. And these dots here indicate where earthquakes occurred. And what's plotted below here is just the number of earthquakes. So this is just the total number of earthquakes I have of a given size. That is, how much mass got moved in that earthquake. And what I want you to see is that this scale here is what's called a logarithmic scale. And so here I have 100, here 10, here 1, here 0.1, here 0.01. So this is covering many, many orders of magnitude in size of the earthquake, in number of the earthquakes. And here I have many orders of magnitude in the size of the earthquake. So this covers something like 5 decades of magnitude of the earthquake. So here again is something which we don't understand, but is obviously very important. How do we understand what's happening with these earthquakes? Why do you get some earthquakes which are very, very large, and then a whole lot which are very, very small? And the fact that the number of earthquakes of size m appears to go approximately as 1 over the size of the earthquake, this kind of relationship is somehow the hallmark of a fractal system. So these are some of the fractal objects, and what we want to understand is why should the fractal behavior somehow be ubiquitous in nature? Why should all of these things seem to have a fractal behavior? And it would be very distressing if we had to come up with a different theory for each one of these phenomena, because then there doesn't seem to be any underlying cause for everything to be a fractal. And so that was the object of study for these three scientists I mentioned here, Per Bach, Chow Tang, and Kurt Wiesenfeld, who introduced what's called the idea of self-organized criticality. And actually, if you want to read about this, this appears in the last chapter of the book by Al Gore, Earth in the Balance. I mean, he talks about a self-organized criticality, and he actually gets the ideas pretty close to being completely correct. So I was very impressed. What is the central idea behind this concept? And it's basically an analogy. And the analogy is with a pile of sand. And this is where sand comes into the problem. And what he says is that, or what they say is that if you have a system which, in the steady state, when there's no net change in the system has special properties. It's organized itself to be at a very special point, to have special properties. And it goes in the following way. This is the explanation. Suppose I have a platform, and I take one particle and I put it someplace on the platform. It will stay there. I take another particle and put it at random in another place on the platform. Wherever it's placed, it'll stay. I keep doing this until at some point one particle lands on top of another, and at that point it's possibly unstable. It may not be, may want to fall to one side, in which case it does, and that's going to be what we call a microscopic avalanche. It hasn't moved far, it's just a tiny little thing, but it did move. So I keep adding more and more sand on this thing until finally there becomes a pile with some slope, and now I put another particle on it, and it's on the side of this pile, and because there's a slope, there's more likelihood that if it lands there, it will be unhappy and unstable and move to its side. But the particle that it falls on top of now is also on a slope, and so that slope means that that particle may also be unstable, and so this avalanche is going to grow. And as I add more and more sand, the slope gets higher and higher, and the size of the avalanche is going to grow larger and larger. So this is what happens when the angle is small. Now, suppose you have a very large pile, and you've created it ever so carefully to be too tall, and the slope is too large. Then what happens is if you happen to just perturb the system ever so slightly at the side, what happens is this whole thing collapses. And it brings it smashing down to what's called the angle of repose, the angle where the avalanches have swept through the entire system, the avalanches have been global, the avalanches run across the entire system, and now the system is stable again. So what's happened here is that as you increase the angle of the pile, the avalanches have grown larger and larger and larger until you've reached this steady state angle, the angle of repose, where the avalanches are of infinite extent. They can cover the entire system. And above this angle, if the slope is too big, the avalanches are always global in nature, as they extend out to the largest size that you've made your system. At least this is what the theory is claiming. And so the steady state is just a simple condition where I say that the number of particles that are entering, these green particles on top, falling on this pile, is exactly the same number as are falling off the edges of the boundary of this thing. And that, at that point, you've arranged it so you're at this angle of repose, and the avalanches should somehow extend over the entire range, and they should have small and large avalanches as well. Now, this is the model, the toy model of the sand pile. What excites a physicist about this is that this really means that there's an analogy here. And the analogy is that it's like a magnet. And we know a lot about magnets. It's been something that's been studied for decades now, and we really understand why magnets behave the way they do. And so if you take a magnet, you take it up to very high temperatures, it's no longer magnetic. That is, it's only magnetic at low temperatures. At high temperatures, the spins are all doing what they want, and they're just moving around without really knowing what their neighbors are doing. As you lower the temperature a little bit, a few of the spins start to align with one another, but they're in small little clumps. And as you lower the temperature more, larger regions of the magnet cooperatively arrange until you reach what's called the Curie temperature, the temperature where the phase transition occurs. At that point, these correlations, where these spins are correlated with one another, extend over the entire system. This is what's called the critical point. That's why criticality is in the title of this theory, self-organized criticality. So what the authors had proposed was that there's an analogy between the sand pile, where you're looking at the size of the avalanches, and this magnetic case, where you're looking at the size of these correlated regions of spins. And we know a lot about these correlated regions of spins, that they have clumps of spins on all length scales, just like these fractal objects that I've been talking about. And so the analogy goes, there's one mistake here, this shouldn't have a repose here. The angle is what is analogous to the temperature in this magnetic system. The avalanche size is analogous to the size of the ordered magnetic domains in the magnet. The angle of repose, the special angle which is where we're at steady state, is analogous to the critical temperature where the magnetic behavior sets in, where you have magnetic order over the entire system. And so the argument is, at the critical temperature, all sizes of magnetic domains exist, and therefore at the angle of repose, all sizes of avalanches should exist. Okay? The question is, do they? Now, there's a very important aspect of this theory that I want to emphasize, because this is what really makes this an exciting theory, especially for an experimentalist, is that this system is self-organized. If I were going to study a magnet, I'd need a lot of equipment to make sure that I got the temperature to be just exactly at the right temperature within 10 to the minus 3 of a degree centigrade from the right temperature to be able to see all the wonderful effects of critical phenomena. But with the sand pile, I don't have to do that. The system does it for me. Because if the angle is too low, then just no avalanches occur for a while. And as I drop more particles on this thing, the slope increases and increases until you get to the angle of repose. And so it tunes itself, if it's too low, to increase its slope. And if the slope started out to be too high, you would just have one humongous avalanche, which would bring it back to the angle of repose, so that you win on both sides. And so it always brings you back to this critical point. So that's what the argument is that, you know, as an experimentalist, I didn't have to do anything. And as an experimentalist, I don't like to do anything. And so if it does it for me, that's wonderful. Now, that's one thing about the sand pile analogy, but the other thing is that, you know, not that much came into the sand pile analogy. I didn't have to assume too much. I mean, I made this ad hoc assumption about putting particles down at random on this plate, but this could have been anything. This could have been how the sea washes away land from the shore, for example, and you could have made up a similar argument for that, or how globular clusters form. You could have made up another kind of argument similar to in spirit to what I talked about for the sand pile. And so this idea of self-organized criticality could, in principle, be applicable to all of the types of things that I mentioned before, all these as a common explanation for all of these fractal objects. And so the authors had talked about it in terms of the sand piles. I mean, in green, I have here the various geological things that they had talked about: sand piles, coastlines, earthquakes. Then things that are more close to the home of condensed matter physicists, what we've been talking about this week at the conference: charge density waves, 1/f, noise and turbulence. Again, things which seem to have at a more microscopic scale this fractal behavior. But then I think they got just a little bit carried away when they said that life was a self-organized critical system, and then you have to read the paper to realize they only meant the game in the computer, not real life. And finally, when they said the universe is a self-organized critical system, you begin to wonder whether they've completely lost all their senses. But the point here is that, you know, they might be right. And even if they're not right about the universe, suppose they only get 10% of the universe right. That's still a lot of the universe to have gotten right, and it's still a pretty important theory to have gotten that much right. So it's still worth testing. So that's what we set out to do with a sand pile. And the experiment is really quite trivial. What we did is we took a three-sided box with a bottom, and we just started pouring sand from on top. We had some kind of, Rube Goldberg apparatus on top that spread the sand evenly across the whole system. And after a while, you got a wedge of sand. And as an avalanche took sand across the front surface of this box, we tried to detect how much sand got swept across this surface. Did you get small avalanches and big avalanches and all things in between? And so that was the kind of thing we wanted to measure. And so what we did is we just took two metal strips and placed them there, and any sand that fell through the strips could be detected because this is what's called a capacitor, and you can just measure the current that the sand induces as it goes through these two strips of metal. So it's a very simple experiment. You can basically do it with a voltmeter. But there are a couple of problems with that experiment that you should be aware of, and so it tells us something, but you might want to do something more, slightly different to check the results. And one of the problems is, well, how sure are we that we're putting the sand down randomly over the entire system? Maybe we're not doing it quite right, and more of it's landing in one place than in another place. So so that's one problem. Another problem is, how sure are we that the sand that's coming from on top, that's falling onto the system, doesn't have noise in it itself, and that somehow that's really affecting all our results? And so there's another very simple experiment that we can do, a little bit like the first, where we now just take a cylinder, cut it in half so it's a hemisphere cylinder, and put a plate across the bottom half of the opening, and then fill it with sand and just turn it very slowly around the axis of the cylinder. Now, everything is going at exactly the same rate, so that there's no worry about whether we've done something that's not random, because everything is equally likely to have start an avalanche. And we also can pull at a very precise speed, so that there's no worry about how fast we're doing any of this and whether that's influencing any of the rates. Again, we have a pair of capacitor plates, these two metal strips down below, and we can measure the amount of sand that goes through those strips. So these are very simple experiments. And, they're very cheap. I mean, this is, a three-sided box. I mean, a few pieces of plexiglass and sand, $50 max for all of this, except that then you go to a spectrum analyzer, which is $25,000. And, we borrowed that, so that was okay. Now, one thing I should tell you is that we have to worry about a lot of things here. I mean, I'm saying how simple it is, and it is simple in concept, but, we didn't know, does humidity affect all of these things? So we had to do this in a dry box and all sorts of things, so be careful about that. How about the shape of the sand? Does the things depend on what kind of sand I use? And so we use lots of different kinds of sand, and I brought some along so you can see it. This is stuff that's rough. So this is rough sand, and I'll start over here and you can play with it. And then we have things which are spherical grains of sand, and we did this with different shaped sand and also different sizes. And so this is larger sand, and this is smaller sand. And so you can have this there. And we did one even smaller than this, but it's a very fine white powder, and I didn't dare try to take this through the airport security session. I mean, it's embarrassing enough trying to explain all this other stuff that I brought through, so I didn't want to try that. Okay, so what did we see with these experiments? And what we saw was the following. This is a signal that came out of that device. That's a signal. So this is a signal as a function of time. So this is 1,000 seconds, 2,000 seconds, so 15 minutes, a half an hour. And what you see is basically a very flat region background, and every once in a while you see a big spike where a lot of sand flows through your capacitor plate. Big avalanche occurred. And then it goes back and nothing happens, and then another big spike occurs. And then nothing happens, and then another big spike occurs. And if you look at this, the spikes seem to be pretty much evenly spaced. There's no big variation in the spacing between these spikes. There's no big variation between the sizes of these spikes. I mean, this is smaller than this, that's true, but not that much smaller, maybe a factor of 3 smaller. Nothing which is going on many orders of magnitude in size. So this doesn't look like you're getting anything that looks like any of the other stuff I showed you before. That this stuff looks like only one kind of avalanche is occurring. And each time an avalanche occurs, it's a huge avalanche which sweeps through the entire system. And I want to show that this is not a particularly subtle effect. This is something you can see very easily. And so I have a movie of this. So Shebo, you can start that. Okay, so it's called the relaxation at the angle of repose. Okay, and so here we have a drum, and so it's a full drum now, not a hemispherical drum. And around here, and we have a string which pulls this drum around its axis here. We filled it up with sand to this level. The string is attached at the other end to a pulley attached to a motor, so it's going around at a very constant rate. Now, just to show you what's happening, we just pull this rapidly, and you can see the black tape around the side moving, and as I pull it, the sand always brings itself back to the same angle, that is, it keeps coming back to the same point. So now this is a close-up of one little region of that so we can see the flows. And so you see that now it's flowing, flows for a while, then it stops. No question about it, it stopped. Now it goes again, goes for a while, and then it stops again. And then it goes a while again. And you can hear that, it's going essentially in a periodic fashion. That goes and then stops, goes and then stops. And it's not something that's that hard to see. So we can do it with a stopwatch and look at, and actually just time by a stopwatch, the length of the avalanche, the duration of the avalanche, and the interval between the avalanches. And so now we could get rid of that $25,000 piece of equipment, and we just do it with a stopwatch. And so the whole experiment for under $100. Okay. Now, this is a little aside here I want to show you, is that this is the flowing sand. I've just focused on another part of the drum for the moment. And I want you to notice that there's this little white line here. And when this flow goes, it's all the flow is above this white line. You can look at each one of these little glints of the sand below. They're not moving at all. That sand is stuck and doesn't move at all. And so everything moves along the surface of the sand in a surface layer. And then there's a region here which separates it from the bulk. And if you think about this and think about any liquid that you know when it flows, you don't get anything like this at all. That in a liquid, what you have flowing is the whole liquid. You don't get it confined just to a very small boundary layer of maybe 20 particles thick in this case. Okay. So there's no, okay, can we stop it now, Shebo? Okay. So what you saw about that white line was another interesting story in itself, and maybe we'll get to that towards the end of the lecture. So just to show you that we can really get data of decent quality with the stopwatch, I show you here the kinds of data we can get with this rotating drum, that here there's a number of avalanches we get that have, this is a number of avalanches that we get that have a duration of around this a given time tau. It has a peak around 1 second, and the interval between the avalanches is around 50 seconds. Very easy to distinguish between these two time scales, and you can see that, yes, there's some variation in the size of the avalanche, or the interval between the avalanches, but they're not covering a very wide range of sizes. They're all relatively fixed around some common value. So what's going on in this case? Is this an example of critical behavior, or of self-organized criticality? And we would have to answer that this is not what we expected. This is not what I led you to believe with that long song and dance about putting the particles down one at a time and watching the avalanches grow as the size of the particles, size of the slope increased in size. And it's not like what we see in a magnet. We only see one kind of avalanche when it happens, and they're global avalanches which span the entire system. And this is reminiscent of something else that we see, and I want to show you that. And this is freezing of a material. That is, if you take water, you know you can supercool water below its melting temperature. So to show you this, I have something that you may all be familiar here in Aspen. This is one of these called the heat solution. And this is what you carry around in your pocket when your hands get cold and you want to warm them up quickly on the slopes. And it's a liquid. You can see the bubble in there that's moving around. This little clicker in there is moving around. And I claim that this is supercooled. It's below its melting point. And if I now, if I can catch this thing, click this thing, you can see that the crystal now is crystallizing, and it's going through the entire system. And as this thing heats up, as it crystallizes, it heats up, and you can warm your hands. And I have a couple more which I'll pass around starting here. So someone here will, and don't you do it this time, Alan. Okay, so this is an example of another kind of phase transition, the phase transition between a liquid and a solid. And that's what I claim the sand pile avalanches look like. That is, here what happened was that we raised the slope of the pile until you got to a certain point, which I'll call the maximum angle of stability. Once you're above that maximum angle of stability, the avalanche, the sand pile gave way, and you got a big avalanche, which brought this thing back to what is rightfully called the angle of repose. This is the angle that you get after an avalanche has gone through your system. And then you have to slowly increase the size of your system, size of your slope again, until you get back to the theta max in order to get to the next avalanche. And so you see this hysteresis, as we saw in the liquid, the supercooled liquid, where you could cool below the melting temperature. Here, I can raise it above the angle of repose and still stay in one state. And so this is what the avalanches seem to be more reminiscent of, rather than the phase transitions associated with the magnetic change of phase. So the question that I would ask is, can you get back to self-organized criticality in a sand pile? And so one of the things that you might think is, well, can we get rid of the two angles? If we got rid of two angles, maybe we could get it back to the lower angle and we'd be set. And so one way you might think of doing this is by vibrating the sand pile. And so you vibrate the sand pile, and maybe you'll get back to something where you no longer have that upper angle anymore, and everything is going to only occur around this angle of repose, and perhaps, if you're lucky, you'll get something that looks more like what the theory says it should look like. Unfortunately, we tried this. Well, fortunately for us, we tried it. Unfortunately for the theorists, we tried it. And we didn't return to anything close to self-organized criticality. It just looked pretty much the same as what we saw before that I showed you. But then suddenly you begin to see a whole wealth of other new phenomena occurring. And so one thing that you can kind of guess is that if you took a pile of sand, like I just happen to have here, this is mustard seed, and you start shaking it, slowly this pile, the slope would change as you shake this thing. And so you can see that there are global changes in the structure of the pile due to the vibrations. But that's not the only thing, nor perhaps the most interesting of the various things that you can see. And that if you shake this pile, just put vibrations in, you begin to see convection patterns going on, and you can see size separation of, if you have particles of two different sizes in your pile, as you shake this thing, these things will start to separate according to their sizes. So you can play with avalanches for a few minutes. And I'm going to show you some of this, but before going on into that, I just want to indicate some of the other fascinating things that go on in a sand pile. I told you about the boundary layer, where when this thing flows, only a narrow band of the material flows, and it's all confined to a boundary layer, and it doesn't go deep into the depth of the pile. So this is one thing which is really quite strange. It's not like any liquid we know when it starts to flow. But there's another thing that piles have, or sand has, is that if you ever try to take some sand and try to shear it, try to move it, in order to move it, the sand has to expand. And you've seen this at the beach. Okay? Remember when you look at the beach and the beach is kind of half damp, and so you can see the dark part of the sand right above where the sea is coming in? And then you put your foot on a part of this and put your weight on the foot. Remember how around your footprint you can see that it gets lighter, just around that little region of your foot. Well, what happened there is you put your weight on the foot, it made the sand move. Because it moved, it had to expand, and the water drains away from the region where the sand expanded. So this is one example of this thing called dilatancy. What I have here is another demonstration of this, which is very difficult to get past security. I mean, what I've done is I've filled this up with sand up to this level and water up to this level. And the water is above the sand, and if I squeeze it, suddenly the water has sunk below the level of the sand. It drops below the level of the sand because as I pushed the sand together, it had to move. Because it moved, it had to expand. So there's more holes for the liquid to drop into the region below. So, again. So this is one example of dilatancy in granular materials. Another property that, again, you're probably well aware of and see all the time is that granular materials can have many different densities and that they're all very stable. So, when you go to a grocery and you order coffee and the salesperson pours the coffee beans into the paper bag and they fill it too high, they don't pour it out and get rid of the excess. What they do is they just bang it a few times and suddenly they can close the bag. Well, that's because the coffee grounds, or coffee beans, are granular materials which can exist on many different densities. And by shaking it a little bit, it can become more compact, and you can then begin to close it in a smaller volume. So here's another little demonstration where I fluff it up, and it's now at 24. I'll put my finger where the top of the sand is. I hit it a few times. and you see that the thing has dropped by about 10% from where it started. Okay, so this is an example of how many densities are possible, and that's again something that we're not that used to talking about in other forms of matter. I mean, usually water exists in one density, a solid has another density, but it's the same for that solid. That same solid doesn't exist on many different kinds of densities, and we don't really know how to treat the properties of sand when all different kinds of densities could appear in this material. There's another thing which is called arching, and it's the principle behind cathedrals. There's these old cathedrals in Europe, you pile stones together, and you pile one stone on a stone, you keep piling these up, and eventually at the top you put the keystone. And this keystone keeps all these stones from collapsing in on the center. And so you can have these huge cavernous vaults that are held up by these granular material, just these stones, placed in a particular arrangement around the side, and the thing doesn't collapse in on itself. Now, this was done by people trying to design it so that you got huge vaults in here, but in just an ordinary material, you're going to have similar types of things, that there are going to be smaller regions where the sand forms these arches, and you won't get enormous vaults because it's all happening naturally and at random, but you will get little structures in here where all the forces are concentrated, and big regions where no forces are concentrated at all when you try to press down on something. And so I have a little demonstration here which tries to show how this is, how we can see this. And first I want to just show you what I've got here. I've got a piece of plastic in a little clamp, and I have two pieces of polarizer. I mean, so I've got a polarizer on the bottom of this, and then this flap of polarizer that I can put over on top. And when I put the polarizer on top, it's a cross polarizer, so no light gets through. That is, the bottom polarizer polarizes it this way, the top polarizer polarizes it this way, and so no light can get through this region. So now, can I get the lights turned down here so that we can begin to see this? Okay. So now I'm just going to squeeze on this clamp, and you can see that as I squeeze this thing, I can now see through the region where the plastic ball was. Because the plastic ball being squeezed changes its nature so that now it actually rotates the polarizer, the light that came polarized at one side, rotates it by 90 degrees so it can come out the other polarizer. And so we can see where the ball was, the ball that was being squeezed. Okay? So this is the principle behind how this experiment was done. What was done here was we started with, or not we, this group, done too, at all, where you filled a container with beads, glass beads, and you had a piston here which you just pushed down on this top of this container. Before you put any pressure on here, you couldn't see through this container at all because you had cross polarizers in back and in front, and nothing got through. But then as you press down on this force, you can see which beads contain all the stress. And they light up like a lantern here, and so, or like a Christmas tree. And so you see all of these paths where the stresses are now going out into all directions. And so it's not homogeneous. There's regions in here where you have big empty spaces, but then you see these paths that continue all the way out to the boundaries. And in here, again, you see all of these different paths where you have concentration of the forces and big regions where no forces are being felt at all, and these are like the arches. And so these arches now is, again, something that we don't know how to deal with. They're new to us, and we're just beginning to try to ask, well, what do they imply for the behavior of a sand pile? Okay, and so now what I'd like to show you is these last two things, the convection and size separation. These are movies now that were taken simply by taking a container of beads and vibrating it vertically up and down. That's all we're doing to this system. And so can I have the Okay, so here is a container filled with beads, and I'm just vibrating this thing up and down vertically, and you can see suddenly you get this big motion of all these particles, just like a spaghetti pot boiling. But all we're doing is vibrating this thing, and it goes rushing down the sides, on both sides, and goes on up to the middle, and actually forms a heap of this thing. This is a heap that's generated by the vibrations itself, not by not by hand externally. Here we've done the similar thing in a circular geometry. And you can see now the sand is rushing up the sides of the circular geometry and come barreling down the top of this container. Okay? And again, all we're doing is vibrating this with just basically a loudspeaker from below. And now you'll see it comes down, then you get this convection around here. You get these rolls that's really just churning around in a very frenzied loop at this side, part of it going this way and the other part going down into the center of this circular container. Okay. So now we've made a layer cake for you, so you can see these two things, and we're going to start vibrating this thing. And so you can see that the black parts start to move up into the white region. This is a low acceleration that we're moving this thing, and now you suddenly see the black stuff has come out through the top and is moving down these sides here and down here, and you're getting this confined to a top layer at a relatively small acceleration. And as we turn the acceleration up, which we'll see in a second, you'll see that this region of the mixing starts to occur farther and farther down. And this is something that is just, I mean, I find phenomenal. You can just sit and watch this thing mesmerized for hours, watching this stuff go around and there we go, in circles. So you can see it's, again, barreling down the sides. It's nice and symmetric here, with all of this stuff moving up towards the center, flowing out to the sides here, and down the boundaries of the system, and then start to move up towards the center again. So this is something that's convection, which is just created by the vibrations. Now, what I want to show you is in a three-dimensional geometry, we just take a cylinder of material. We put in small spherical beads, and then we put in some colored beads so we can mark what's going to happen. And these beads are all the same size. And now we're going to drop one large bead in the middle of this, and it's surrounded by the darker blue beads. These are mirror images of this, so we can see all three sides of this at the same time. And now we fill up some more of the light-colored beads on top of this, so that we're going to get a sandwich of the big bead in the center of this tube with a ring of dark blue beads around the side, and then above it is another whole region of the colorless beads, and below a region of the colorless beads. And now we start to shake it again in discrete taps. You can see the outside stuff is starting to fall like a rocket. The inside stuff here you can see is beginning to move up the column of the container, the cylinder. And now we just focus on the top, and there is the big bead coming out the top. And this is a well-known phenomenon. I mean, you see this all the time whenever you open your cereal box. Your cereal boxes, you get all the good stuff at the beginning of your of the day, and then by the time you get finished the cereal box, all you get is this little grunge stuff at the bottom. And that's not particularly nice, and that's something that ubiquitously happens in these granular materials. Here we've put some red stuff on the top, the same material, just to show you that the stuff falls down the sides here. And this is actually something that we hadn't known before. This is the, from this picture, we realized, well, what is creating, I guess we can turn this off now, Shoba, thanks. What's creating the motion of these large beads to the top is the convection. That is, all those small blue beads came up with it. It's a whole convection cycle that the large bead gets carried to the top with all the small beads, but then just gets left there because it can't get down in that very small region near the side. Okay? So this is at least one mechanism for this size separation. Okay, so this is kind of the end of the properties that I want to tell you about sand, the end of the talk. What I hope that I've shown you today is some of the fascinating physics that can be seen in just a simple sand pile. And there are a lot of intriguing phenomena. For example, these things I just showed you about the convection and the size separation, which is really somehow unique to these granular systems. You don't get the same kinds of things in an ordinary fluid. But there's also, the first part of the talk is what I was trying to show you, is that there's a possibility of using the sand as a metaphor for understanding other types of physics. And even though I don't think that the sand helped us understand the fractal nature of the universe, that is, these fractals, because I don't think the sand avalanches were really fractal, it did give us a handle on looking at the theory that had proposed that. And that there's a feedback between the experiments that we're able to do on these simple sand piles and these theories that purportedly explain some rather dramatic effects that affect, much larger systems and a much more basic phenomena in the world. And so moral is that even sand piles can be have a lot of basic physics contained in them. Okay, thank you for your attention. Oh, the line, I'm sorry. That was this question of this size separation. See, what had happened there was that there was some small dust in the sand, in that container that we had. And as the avalanches occurred, the big particles were moving, all the top layer was moving, and all the dust filtered down to the very bottom of the moving layer. And so it formed the small particles were at the bottom of where the motion occurred, and then they just stayed there because they wouldn't go down below that. And so this was just a simple marking device for showing where that boundary layer actually existed. You can do the same thing without the dust in there, and you'll see the same thing, but this made it particularly easy to show on a video.
I've noticed when you watch water sheet down a roadway or a flat surface, that it will pick up a pattern to it. It doesn't have just a constant sheet to it. There's a kind of a lenticular pattern that's formed. Does that have an analogy with your avalanches?
I don't know if actually, there are people here at this conference who know a lot more about water flowing down surfaces than I do. That people have used the word avalanches to kind of describe some of the same phenomena. I don't think it's related to the same kind of behavior that we've seen in the sand avalanches, for example. That there you do see the water sometimes breaking into many different rivulets, and so that this may have something which does have at least some different length scales involved, but you have now gotten all my wisdom and more on the subject, and I should leave it to the experts to tell you more about that.
Not a road analogy, you get washboard, and I'm just curious how it gets started, because you get this one bump, and then all of a sudden you've got like a road about 30 miles. It's kind of irritating to drive over.
It's very irritating to drive over them, and my personal view is that General Motors goes there and digs out these things so that they can replace your car sooner. But again, that seems to me to be a question of resonances. Of your car starts to this natural resonance of your car for when it goes up, and then as it comes down, it tends to want to make another rut in the road. And so, because cars have natural resonances of that size, then you're going to get that thing repeated over and over again because of the structure of the car. If you didn't have the car going over it with its particular mechanical properties, I wouldn't guess that you would have that. Mm-hmm.
And it starts and then it stops. Does it really stop and start, or is that just something that we're seeing on the film? This is the actually happens all the time.
No, this was of the whole thing. So where is the mustard seed? Can we, mustard seed. Can I get my mustard seeds? You'll get it back. So here's something that you can see the whole thing at one time. So the question was, when I showed the blow up of one little section on the movie of the Avalanche, I didn't show the whole thing going. And does the whole thing stop? And the answer is yes, the whole thing does stop in this. And I'm going to try and do this slowly, and I hope my hands aren't shaking. And you can see that the whole thing is stopped. And now the whole thing moves. Now the whole thing is stopped. Now the whole thing moves again. So it's not just because I focused on a small little section of this, but it really was a global thing that spanned the entire system. And the way to make sure that that happens is I have to make sure I'm rotating this slowly enough that another avalanche doesn't start before this one stops. And so that's the one question. Who does this belong to?
You get an average angle of repose across different grain size, and I mean, is there like a single answer to that?
No, that is, the angle of repose varies from material to material. They're on the order for these things that we studied, they're on the order of 30 degrees, but some are 25, some are 35. So that number is not something that's universal. That's going to vary depending on your system. But we have not yet found anything which doesn't have these two angles. That is, the difference between two angles may change, and the exact value of the angles may change, but you will always have that general result that there are two angles, and you have the maximum angle of stability, and there's the angle of repose, and you go in between those two. And we've done this with very different sized particles, shapes of particles, not just the ones I handed around, but we tried rice. You know, rice is nice, long, cylindrical things that they have to tumble to go down. And there again, you can see two angles in that case. But again, very different angles from what we've seen here.
Could you please speak more loudly so the rest can hear your question?
Okay. In the film, you showed the rate of rotation of the cylinder at 3.2 degrees per minute or something like that. Is the rate of rotation affect the two angles that you get? Both the angle of repose and the angle at which you avalanche?
No, that is what we've... one thing, again, with my little gizmo, which is going around here, the mustard seeds, if you turn it too fast, you're just going to get one continuously going avalanche. It's just that before one avalanche has really had time to finish, the angle has gotten big enough so that the next one has got to start. And then you're going to get into a very complicated regime where something is continuously flowing. But as long as I go below that region and I get discrete avalanches happening, it doesn't really matter how fast I'm moving the rotating this drum, and that I will continually get the same two angles independent of the speed of rotation. So in that part at least isn't varying.
But you did that, like you did it at a slower rate than what was in the film, and you still got the exact same angle?
Right.
With the rotating drum, do the granules that don't move at all, that don't take part of the avalanche, they tend to be the smaller granules?
No, they're just below that angle. I'm sorry, they're just below the boundary layer. Eventually, they will, as I keep turning this thing, they will get to the top of the pile, and then they will participate as well. And so eventually, as I've turned this thing around by 360 degrees, all the particles have participated in the avalanche, probably several times, but they just don't participate on each avalanche. They just, if they're not near the surface or close enough to the surface, they don't participate at all. Yes.
Yes, wouldn't the differentiation by size through the vibration more to the different inertias of the particles and the actual physical size of the particles?
No, that is, we can do this experiment with different, all sorts of different kinds of particles in there. These ones that I showed here were done with exactly the same kind of glass, so that the beads had the same density, whether they were small or large. You can also change the kind of material you have in there, and make, let's say, the larger particle less dense so that it has the same mass as a smaller particle, but it's just bigger. In both of those cases, you still get a tendency for the large particles to go to the top. Now, eventually, everything is going to break down. That is, suppose I put a neutron star in there. There is no way I'm going to get that to the top of the thing, because there's going to be another force that's just going to be pulling this thing down to the bottom of the container. Okay? But what this is showing is that if you have things that are of comparable density, a very strong force is trying to make the larger particles rise. And so that's independent of these other phenomena which can also occur. I mean, there's certainly, in the movies, you saw two other kinds of segregation. One is due to the density, as you're implying, that's the inertia, or basically the density, the mass of the particles. But the other thing is that if a round particle or a faceted particle, something that's rough, they're going to try and segregate into themselves. That a rough particle is not going to try and move as much as a round one is, because it's got to scrape against all its neighbors and it's impeded from its motion. And so, again, you're going to get a kind of segregation due to that. So there are a bunch of different segregation mechanisms, but one of them, or probably the most important for these systems, is just due to the size. No, we haven't done that, but you're alluding to something that's really kind of interesting about sand, which I didn't tell you about, which is, why doesn't hourglass work? I mean, why didn't people make hourglasses out of water? I mean, why do people use sand in an hourglass? And the reason is that, if you take a tube of water, the pressure that you feel at the bottom is proportional to the height. That's the pressure head of your, due to the water. And so the taller you make your tube, the larger the pressure is down at the bottom. That's not true with sand. That is, if I take a cylinder that's a mile high of sand, and I fill it up 1 foot, and I measure the pressure down below here, and then I fill the thing up to the top of the mile, I will see exactly the same pressure down at the bottom, irrespective of how high I filled this hourglass, or this tube. And so, that's why you leave your pets at home with the pet feeder, which you put the dry dog or cat food in and then you turn it over. And why do you fill it way up, and why doesn't it come spewing out all over the floor? I mean, the cats do it, but it itself doesn't do it. And the reason for that is because it doesn't matter how high you fill this thing, because the forces are all held by the external walls of this container, not by the other material in it. And so it'll only come out to a certain height.
When you were showing the vibrating masses of particles, I noticed it wasn't obvious what created the shape at the top of the tile, and I was just wondering if you had a way of accounting for that. I can have a hand-waving way of accounting for it and a serious way of accounting for it, and I don't have a serious way of accounting for it, and so all I can give you is the hand-waving way. And what it is that what's happening in the shaking of this thing, that you're forcing the particles near the side to start moving downwards. So you're getting a flow down, and you've got a return flow that's moving up, okay, towards the center. Now, and so you saw that in the tube. That is, the flow around the outside moved down, and you had the return flow going back towards the center. Well, the only way that you could have that balance is that if the center gets higher, so that then the stuff can then start to flow down and form a cone from the center of the tube out to the side. So this is it's a question of looking at the, you have a conservation of current in here of where this thing goes in the steady state, but to actually analyze this and find out, well, what should that angle be, that's a very different question and much more difficult.
For what it's worth, looking at the pictures, that explanation doesn't do it very well, because I remember one of the pictures with a square bottom, you had a slope on the top. It just went from one side.
Oh, okay. Now you're getting into the dirty laundry. I mean, this is because of what's happening in that case is probably that the vibrator from below was not vibrating this thing completely uniformly across the entire system. Okay, so if it had been completely uniform, we would have probably gotten the peak in the very center of the tube.
Why did the silo break?
The silo broke because the way that you design silos, or they have been designed in the past, is for very cylindrically symmetric flow. And so you have flow that's cylindrically symmetric, and so a cylinder now holds, has equal forces going all the way around, and that's a very stable configuration for stuff that's, where I don't have anything going out to one side or another. But what we've seen in here is that you can get very nonlinear effects where the flow is not going to be uniformly cylindrical. The part is moving, one side starts to flow first, and then the other side gets hung up for a while, and then it starts to flow. And so this thing is, on average, maybe cylindrically symmetric, but at any instant of time, you've got more flow from one side, then from another side, and then a little bit later, this side versus that side. Now, that creates stresses in the external walls of the silo that it wasn't meant to hold. And so, you could have always made the silo much bigger and stronger and kept anything from breaking, but these were designed for cylindrically symmetric flows, and we now are beginning to learn that they don't have to be in these kinds of systems.
Have you tried these experiments up here to see if altitude affects the angle of pose?
If I get invited back, I mean, that would be a wonderful thing. But no, I haven't. I mean, I don't think air pressure will affect most of the things. What you have to worry about with this stuff is, and I've neglected it completely here, is that there's a second fluid here. That is, I've just talked about the granular stuff, but there's air surrounding all of this. And does that air affect the flow of the grains? And for many things, you can neglect it. For some things, you might not be able to neglect it. And so that's a whole new situation.
Using your rotating drum example, did you measure the thickness of your surface layer on both the uphill and downhill sides? Were those the same?
No, we didn't do that for the drum because the drum has very strange boundary conditions at both sides. And so you have to worry about that. The best way of trying to look at what the real boundary layer is not in this configuration, which is easiest to see, but is in what's called annular disk arrangement, where you fill it in an annular disk and you have everything is basically symmetric, and you rotate this thing around in a circle, and then you can see how far down the particles start to move. And that would be a better way of getting what for a given rate of motion, how a large boundary layer is going to be.
Is it correct to say that the sand system did not display a fractal system? And are there other systems being experimented with that do display a fractal system?
Well, look, there are plenty of things which display fractal behavior. You're absolutely right. The message of this talk was that these avalanches did not look like they were displaying really the fractal nature that had been proposed to them. One thing that I don't know yet is when I showed those arches in there, when you push down on the beads and you saw the rays go out, that looked like some kind of tree-like structure which may be fractal. I don't know. That hasn't really been studied. But we certainly know that there are a lot of systems which are fractal. We just don't know if there's an underlying reason why all of them should be fractal. And that's what this kind of model that I talked about, this idea of self-organized criticality, was meant to show.
There's a sand dune park down in the southern part of the state, and when I was a kid, I played it just once. And I remember jumping off the tall sand dune hills and landing and hearing it was like rubbing your fingers across corridors. It was a very rhythmic sound when you hit the sand on the low end. We never could figure that out. Can you shed any light on that?
There are, there are a couple of things that have been talked about with these things. One is called the singing dunes, where you get this low, roughly an A tone coming out of some dunes when it gets excited. There's another kind of sound which I think is a higher pitch sound, more like this squeak that you, I think you're talking about. Or
It was a very rhythmic, but on a much larger scale.
look, I mean, I have a theory for it. I'm not sure anyone else accepts it worth a damn. So, but I think what's happening in that case is that if you look at the simplified version of a grain of a sand pile is I have beads, which are my fingers, and they have the next layer of sand, which is another set of beads, and now they start rubbing over each other, and they're going to fall into the depressions below, and then get raised, fall into the depressions, raised, fall into the depressions. That falling into depressions is going to be a rhythmic sound that you hear as this thing. Because all the sand is roughly the same size, so you're going to hear that from a large region, all of those things happening in unison. So that's, someone agrees. Okay.
If there are no more questions, let's thank him for a very...
for some things you might not be able to neglect it. And so that's a whole new